Hello everyone, I'm Amin, and today I'm going to talk about how we are using TensorFlow at a scale at Unity Mobile App Network. But before getting started, how many people know what Unity is? Okay, pretty good. And how many people know what a mobile ad network is? So the mobile ad network is basically that tiny annoying thing that you need to watch when you want to get extra lives in a mobile game. So let's just make it clear at the beginning. So basically, Unity is mainly known as being a 3D engine in order to create games. Mobile game, AAA games, whatever you have in mind. And in the case of the mobile game, when the developer is basically developing the game, they have a tiny box to check in order to monetize their game using Unity Mobile Ad Network. And that basically means that they want to show ads and earn money by showing ads in their game if they check such a box. So that's the mobile ad network created by Unity. But Unity can be also used for other stuff, like creating animations or creating automotive videos, creating like architecture, structure stuff for the simulation purposes, and recently better known for ML agents that some companies like DeepMind use in order to perform simulations and train reinforcement learning agents. But what are the major data science problems that we have in a mobile ad network? So in a mobile ad network, there are two main players, and I'm going to talk about them a lot. So we have the advertiser, or people who want to show the ad, and we have the publishers, or basically the games that they show the ad. And in between, there is Unity. But what are the problems that we are trying to solve? First and foremost, we need to know what is the probability that these users install the games if we show the ad. The second thing is that advertisers might be interested in higher quality users. So we need to know what is the expected value of the user in their games. And the expected value of the user is basically how much money they are going to spend in the game. Some advertisers might let us charge them more if we are able to find that good users. I mean, some numbers are like, some advertisers are ready to pay up to $30 and $50 in order to find a good user from tier 1 countries like US, Germany, and other countries. And then we also need to solve another problem, because in a mobile ad network, it's a matter of bidding. So there are other ad networks that they bid on the same user. Unity is one of them. We have Google AdMob at the same time. We have AdColony, we have Ad Choices, and many other ad networks. So we need to know, if we think that the user is going to install the game, how much money we want to pay on that. And last but not least, we have the problem of exploration and exploitation. And I think everyone here knows what that is. We know that we have an ad that everyone install the games. But the question is that how many times we should show that ad, because people install that and we exploit that ad. Or how many times we should basically go to new ads and try to show them or explore the space. And here we can see what is an ad network in a glance. On one side, we have the advertiser. On the other side, we have the publishers. Advertiser want to find good user. Publisher wants to make money by showing the ads. But here is a catch. And the catch is that the publisher and Unity are going to be paid if and only if the user install the games. So it is not just a matter of showing the ad. It is a matter of showing the right ad to the right user so they can install the ad, or basically install the game showing through the ad. So both Unity and the publisher can make money. Otherwise, if an ad is shown and user is not going to install that, nobody gets any money. So this is basically overview of the system that we currently have. So we have our data, we have all our data basically stored in Google Cloud Storage as Parquet files. And we have data proc clusters, which are basically Spark clusters in Google Cloud, that are orchestrated by Airflow. So they will go and read those Parquet files, and then they will generate the required data for different networks that we have in production. For example, the network for convergence prediction, the network for interest-based targeting, the network for in-app purchase interest-based targeting, the network for retention, the network for depositor. And some of these networks, like interest-based targeting that I'm going to talk about today, are going to be auxiliary networks that are being used in the production models. And when the data is ready, some TF records files alongside the JSON files, we have Kubeflow jobs that consume those data to train those models as TensorFlow hub modules, and they also write some logs in the Cloud Firestore. By the end of the day, when those models are ready, we have a final Kubeflow job that combines those models, save them as TensorFlow saved model, and push them to production to be served by TensorFlow serving. And we have other services that use these auxiliary models as well. What is the data scale that we are talking about, and why I call it TensorFlow at a scale? We reach 1.7 billion devices each month on average. And on average, we serve 11 billion ads. These 11 billion ads each month being served, it means that per second, we receive thousands of ad requests from different thousand users. And for each user, we need to calculate prediction for, on average, like thousands of games. So it means that each second, you need to be able to do the prediction for millions of these ad requests. So the thing is that if you want to do that using neural network, your only choice that you have is TensorFlow, from the infrastructure to serving and production. Well, PyTorch is trying to catch up, but we should accept it that TensorFlow is the only solution currently. And now here comes a little bit more technical part. So I told you that we have auxiliary networks that are being used in our final convergence prediction network. And one of these networks is IBT, or interest-based targeting. So what is interest in our case? The interest of a user in a game is defined by the number of the ad requests sent by the user from that game. Say a user plays a game, and from game 1, it says 10 ad requests, like accumulated through the year, and from the other one, it sends like 50 ad requests. And we say that, okay, there is a great chance that the user is interested in the second game more than the first game. And this is the interest of the user in our case. But there is a problem. We have thousands of games, and each user can play only a fraction of them. So by definition, this representation is super sparse, and we cannot use as it is defined in a neural network. So what is the solution? What if I can find a projection to a lower dimension, which is dense, and can be easily used in another neural network as embeddings of the user? Well, that is doable using autoencoders. You can do that using autoencoders by easily try to find the lower dimension that you have in mind using the encoder part, and train the network by the reconstruction of the user that comes out of the decoder part. And then basically train the network between the input and the reconstruction. And if you are able to do that, you can represent all your user in lower dimension. And here is a disclaimer that this is not a statistic thing. This is not an offline thing. It is not like we create the embeddings for all the users, save them in a database, and catch them when we need them. The whole encoder part of this network will be used in another network. So that other network can calculate the embeddings on the go when it is required in prediction. So the challenges, I've mentioned that several times. The data is sparse. And data being sparse creates lots of problems for us. The first problem is that we need to change the way we think about storing the data. It is easy. You can use TensorFlow ecosystem. It is basically a one-liner. And later, you can parse that data as variable length features, or as TensorFlow likes to call it, tf.varlen feature. But the problem is that when you basically parse your feature using tf-varlen feature, the outcome is going to be TensorFlow sparse tensor. There is a more serious question. How should I train a network that is capable of training on sparse data? I'm going to address all these questions in the rest of the talk. So what is the setup for deep IBT? We have the Parquet files stored in the Google Cloud Storage. Then the Dataproc cluster is going to consume that data using PySpark, and will create some JSONs and TF records. How many people know what TF record is? So basically, TF records is a data format that can be really, really fast consumed by TensorFlow. So faster than whatever you have in mind. If you want to train your model fast, you need to find a way to save that as TF records. And afterwards, we are going to use a combination of Keras and TensorFlow in order to train the model. And by the end of the day, when we want to ship this trained model to be used by other models, we are going to use TensorFlow hub modules. So let's get into the details. Input generation pipeline. We are going to read the raw data from the Parquet files. We are going to use TensorFlow ecosystem to write that data. But what is that data? What is that data? I told you that in our case, the interest of the user, or basically the way that we represent the user, is a mapping from games to the ad request counts from those games. So in order to represent a user, we need to save the game IDs and the ad request counts from those game IDs for each user. On top of that, on our training set, we are going to calculate some statistics that can be later used during training. For example, we are going to calculate the quantiles of the number of the games played by the user. I'm going to tell you later how we are going to use that when we are training the network. But this is basically the way that we generate the data. And then we do some feature preprocessing. And the way that we do the feature preprocessing is that if a game has not been seen in our data set above a predefined threshold, we are going to map those games to the unknown ones. This is the main part of the feature preprocessing in this case. People might think about feature preprocessing as whitening the data, basically zero mean unit variance of the data. But for some reasons, we are not doing that for the time being. But basically, this is your input. So when you are reading the data, you are going to save the game IDs, which are basically this. Just assume this as a three people batch size, so a batch size of 3. So these are the games played by these 3 users. And you can see that, for example, it says that user 0 has played these games. And then this is the ad request count for that game. And then this is the output of the feature preprocessing, one single sparse tensor, which says that user 0 has played this game with this value. User 1 has played these 3 games with the next 3 values. But the most important problem that we need to solve is how to come up with a TensorFlow/Keras model which is able to train based on TensorFlow sparse tensor. There are a couple of ideas that might come to your mind. The first idea, which is the most naive idea, is that let's explode those sparse tensors to a dense representation and push the dense tensor through the network. Yes, that's definitely doable, but that comes with a price. You need to reduce your batch size, because otherwise you are carrying lots of redundant zeros through your network, which is going to be loaded to GPU, and you easily get out of memory on your GPU. So this means that we needed to reduce our batch size to less than 1,000, and each epoch took around 6 hours. And for such a network, we need to let it run for at least 100 epochs. So this is not basically doable at all. The other solution for the audience that might be more into Keras is that you can define your input layer in Keras with a flag called a sparse tensor. But sadly, that's not how Keras works. So Keras does not expect a sparse to be true to receive a TensorFlow sparse tensor. It accepts another form of a sparse tensor, but not TensorFlow sparse tensor. So we needed to become creative. We needed to think out of the box. So the way that we do that is we are going to create 2 different input layers. One is expecting the mapping. One is going to expect the games played by the users, and the other one is going to expect the counts. And both of them are TensorFlow dense tensors, and Sparse is happy with them. As we go on, we will recreate that original sparse tensor that came out of feature preprocessing through a lambda layer. And then from there, we will implement another layer, which is basically pretty fast in doing sparse dense matrix multiplication, because by the end of the day, you need to do that in order to train your network through the first layer. So in summary, send the indices and the values to different inputs, then through your lambda layer, recreate that sparse tensor, then create a custom layer, so you are able to do that sparse by dense matrix multiplication pretty fast, and afterwards, it is going to be a dense tensor in your network, and your network is happily can go down. The thing is that with this method, we were able to reduce the batch size, to increase the batch size to 20K, versus 1K, which used to be if we wanted to explode that to dense. And the training time for 20K is only 10 minutes versus 6 hours that was with exploding to dance. Well, there is another caveat here that this representation does not work with Keras multi-GPU, but Keras multi-GPU is no good. So do not waste your time on top of that. There was another trick that we were using. That was, we were only training the encoder part of the network. And we basically transposed the weights and used them in the decoder part of the network, which basically reduces the size of the trainable variables into half. And it was learning a better representation or reconstruction of the user. But there is one final missing piece. What about my loss function? How should I define my loss function and keep it still convex? The thing is that, say that we have a binary network. So basically, a user has either played a game or has not played a game. And then in this case, if you ask your network to only reconstruct the user representation using, for example, say binary cross entropy, your network will learn to only generate zeros, which is not necessarily bad. It is the way that your network tries to reduce the loss. The thing is that that's not interesting for us. So you need to force your network to learn to generate non-zero elements. And the way that we do that is basically by creating a masked version of the binary cross entropy. And that is not nothing fancy. The thing is that we only concentrate on the non-zero elements and then calculate the binary cross entropy on top of them. Or in this case, for example, MSE on top of them. And so the masked binary cross entropy calculates based on these two guys. The whole binary cross entropy will be calculated on the whole user reconstruction. And the thing is that we connect these two pieces using a linear relation. So basically, you need to learn a hyperparameter to see how much emphasis you want to put on this loss, on which loss. There is one last thing that is penalizing the outliers. There are lots of bots playing these games and sending ad requests, and there is a chance that we see a user who has played like 2,000 games, which is impossible. So those quantiles that I talked about came into play here. The further the user goes, the number of the games played by the user deviates from the predefined quantile, say 15th quantile, the more the algorithm is going to penalize that and will try to avoid reconstructing that user. Because the thing is that if you do not do such a thing, your network will try to deviate towards those users, because by being able to reconstruct a user who has played 2,000 games, it will try to reduce the loss better than trying to learn like normal user who plays only 2 games. And there you have it. Basically, using this loss function, you can train your network. So let's look at some results. This was the first version of the network that we pushed to production. So we assumed that each user, basically the number of games to be 6,000 unique games, and then reduce that to 1,024 and 512 and then 256. So your code layer is going to be 256. And then your decoder is going to try to do the reverse. So we had 6,000 unique games. Each user played only 4 to 5 games. That means that the data is super sparse. And then the training set was containing 50 million users. The validation set was 40 million users, and the test set was 7 million users. And this is the result. Those red dots that you see are the games played by the user. These all blue stuff is basically the reconstruction of those games played by the user. And as you can see, the network has been able to reconstruct this stuff, which might not be really correlate to any of the games played by the user. But by the end of the year, this embedding is trying to work as a recommender system. So this might be the way that the network thinks about the games that the user might be interested in. And there is one more interesting figure here. The user played 4 games, and these are the reconstructed value for those 4 games at the end of each epoch. As you can see, when we go through the epoch, the network has been able to learn to increase that value until it is able to reconstruct that totally, or to the best extent that it can do it. And as the last slide, some learnings. The best way to ship a model in a way that you want it to be a living model and live inside another model, is using TensorFlow Hub module. And I just call it transfer learning. So the thing is that if you want to ship this model, but you do not want to train that, so no gradient needs to go through that weights of that network, you might need to create the graph again and change those variables to constant. This can be pretty vital in the case that you are using a tool like Google Cloud ML engine, or being called AI, I think, these days. Because in the distributed training, in that case, there is going to be a parameter server. And then in that parameter server, all the weights will be accumulated in that parameter server. So if you are not planning to retrain this model there, it is better not to put a huge matrix in that parameter server. Otherwise, you might crash the whole training process. The other thing is that if you are doing this transfer form of the learning using Keras-saved model, because it is also a valid option, but pretty prone to error, you need to always remember that the cross has been designed in a way that the regularizers, for example, the losses defined on layers, like KL divergence and everything, is a layer attribute. So it will be transferred to the network, to the destination network. And if you are trying to compare this destination network containing this transferred network and compare it using some metrics, say log loss, to a network without that transferred one, you need to be careful because the transferred network, the model that contains the transferred network, will also add those loss to the, for example, whatever loss function you have in mind. And then the loss cannot be comparable with the network without those regularizers. And the last thing is that always start with something pretty simple, something that you're confident. Otherwise, always let's try to keep in mind that this whole data science and these huge projects, they need to be iterative. There is not one shot. There is no one-shot solution for them that you can create your best bulletproof network in one go. And that's it. Thank you.